thanks for the introduction. So I'm a PhD student at Indiana University, and with my advisor, Ryan Newton, who is also here today, we have been doing some research on super compilation. And in this talk, I'm going to give an overview of super compilation and what is interesting about it in the context of Haskell, what is the motivation, like as a Haskell programmer, why would we be interested in super compilation. And I will give an overview of how it works. And then I will ask the question, where's my super compiler for Haskell? And I will talk about my preliminary work. So super compilation in the most high-level sense is, in super compilation we evaluate programs in compile time, and by doing that we make the most out of known inputs and definitions. So if we import some modules or use modules from other packages, we use definitions from those packages, and we evaluate open terms, because most of the time when you compile programs in evaluate programs in compile time, we get stuck in a couple of steps, and then we go on and evaluate sub-expressions. So why is it interesting? Because in a sense, it is the ultimate optimization. It's a whole program optimization, and it's evaluator-based super compiler optimizes in the sense that, let's say I have P1 and P2, and they are semantically the same programs, except that P2 evaluates in less number of steps, and by steps I mean operational semantic steps here. Then we consider P2 optimized, and this is an approximation but works well in practice. So most of the time, in that case, P2 runs really faster in runtime. And this is an approximation because it's very unlikely that all of the rules in our operational semantics have same costs. So this way of optimizing programs, it's a very general optimization technique, because it's basically more general than deforestation, partial evaluation, and call pattern specialization. And there it does a couple of domain-specific partial work of domain-specific partial evaluators, in the case of optimizing SYB or optimizing generics is easy papers. And it does many more optimizations. So in the context of Haskell, we have this great PhD thesis from 2013, and it shows some great potential. Like sometimes it optimizes some programs so that programs run 20 times faster, and in some cases it eliminates all the memory allocation in runtime. But it has some problems that are inherent to super compilation. For example, this is quoted from this PhD thesis, and it says basically we don't super compile the whole no-fib test suite, benchmark suite, because it takes extremely long. And we have another PhD thesis, which is probably published in same year. And it focuses on super compilation performance, but the best it can report is under 3 seconds for some small programs from no-fib. And they also report some extremely low compile times, like 132x compile times, and the generated code size is generally bigger. Yes?
What's a small program?
Yeah. So I don't know actually, but in the PhD thesis they list which programs they use. It's some subset of no-fib. So that PhD thesis from 2013, it laid out a great framework for super compiling, and it describes the super compilation in terms of these steps. So the first step is driving, and in that step we take semantics preserving steps. Sometimes this is operation semantic steps, like we do beta reduction, and if we know constructor in a case expression, then we choose the branch. And it does some additional steps like case-of-case transformation, which leads to a lot of other optimizations. And the second step is splitting. And splitting is what we do when we are stuck. And it happens all the time, because in compile time we don't know values of some variables. So in that case, we keep evaluating sub-expressions. Like if we have a case expression, we evaluate branches. If we have function application, we evaluate argument, for example. And we do some information propagation, and I will talk about that soon. And splitter also does, so after evaluating sub-expression, we need to combine results to form the final expression, and splitting also helps with that. Next step is matching, and the matching means So we evaluate open terms, and most of the time it leads to loops. So a matcher tries to detect loops so that we can form a loop instead of keep evaluating our term in compile time. And the last piece is termination enforcement. So we can detect all the loops because perfect matcher is not possible, and some programs just loop. So in that case, we need a termination enforcement policy, and this is the last piece for super compilation. And here's an overview of how a super compiler could optimize map of map. So the first line is our initial program, map of map. And if you don't optimize it, it generates intermediate list. So a super compiler, so we are going to take some steps, but we give a fresh name to the term we get after each step. And I'm using prefix H for those fresh names, and H stands for history in this case. This actually takes a lot of steps, so I'm skipping some of the unimportant steps. And so after a couple of steps, we have this H1, which is, so we inline application of dot operator and then do some beta reduction, and it gives us this H1. So after a couple of steps, we get H4, which is, so in this case, this inner case expression is coming from inner map application, and the outer case expression is, comes from this other map. So in this case, we are stuck, but we do case-of-case transformation and then take more steps, and then we get this A6. So here, we have case A, and we can evaluate this because we don't know the value. A splitter helps here, and we start evaluating first sub-expression and second sub-expression. So in the first case, it's already a value, so we can't do anything with that. In the second case, this is already in VCAD normal form. But in super compilation, we don't care about that, and we keep evaluating sub-expressions. So we first try to evaluate this first sub-expression. And we can't evaluate that because it's, we don't know F, we don't know G, so we can't do anything with that. But in the second case, so while we are, so we try to evaluate this one, but at this point, nature tells us this term looks like one of the terms we have seen before. In this case, it's the term in H1. And so basically it tells us if we keep evaluating this term, then we end up looping. So matcher in this case tells us how to form a loop here. And so in our next step, we have a new loop which doesn't generate an intermediate list. So so that gave an example of like most of the steps except termination checking. So each of these steps have hard problems to solve, and I'm going to give some examples. So splitter has this problem. So let's say we are propagating too much information, and what do I mean by that? So here we are going to compile, super compile this B and C pair, and while super compiling B, we need definition of N if we want to take some steps in compile time, and also fib. But if we pass definitions of N and fib while evaluating B, then, if we also do the same while evaluating C, then we may end up with this. And in this case, we start evaluating fib of 100. And after a while, so it takes a lot of steps. And after a while, termination checker may tell us, maybe you should stop because it seems like you are looping or this may take forever. And in that case, we generate this residual code with fib unrolled a few times. And we do same thing for C, so we have same definition here, and this is a work duplication. But on the other hand, if we propagate too little information, then we miss some optimization opportunities. So in this case, if you want to optimize, so there's a deforestation opportunity in this case, but if you don't pass definition of map, YS and XS while evaluating this term, then we can't deforest. We can't optimize this term. So this is exactly the opposite of the previous problem. So so the problem with matcher is, so I'm gonna just describe this with an example. So let's say I have exclusive OR function, and the term I'm evaluating is this a pair of exclusive OR AB and exclusive OR of C and C. So one way of supercompile this is, so we can't optimize exclusive OR function anymore. So we generate exactly the same definition. But while supercompiling this exclusive OR of C and C, we may generate this one because matcher, while evaluating this XOR of C and C, the matcher tells us this looks quite similar to your original, to one of the terms you compiled before. In this case, it's this one, except you need to write C for X, the first argument, and C again for second argument. And this is not an optimization, we just generated the same program. But if we force supercompiler to generate, if you force it to generate injective substitutions, then this is how it goes. So in this case, we have a new definition of XOR, which is optimized for same first and second arguments. Because in this case, matcher can tell us that this term looks similar to one of the terms we compiled before, because we can't write C for two different arguments. The problem with termination enforcement, so there are some programs that just loop. In this case, we need to stop. So this is why we need it. And, but sometimes detecting loops is not so easy. For example, in this case, we have a reverse function with accumulator. In this case, so after a while, we take some steps and we get this term reverse, and then H1 comes empty list. So we take some more steps, and then this is our new term. So now our terms, so this loops, but for a matcher, this is not easy to see because our terms are not renaming of some terms that we supercompiled before. So sometimes matcher can detect loops, and in that case, we need to force our supercompilation algorithm to stop. So in 2013 PhD thesis, we have some great solutions to these problems. And the PhD thesis basically documents and implements it nicely, but we still don't have something that we can use today. So my goal is to reboot supercompiler, and I'm hoping to distribute it as a package, downloadable from package, because the supercompiler, it doesn't work well for all the programs, and sometimes it takes extremely long to compile a program. But if we publish it on package, maybe some users may find it useful, or we can use it for research purposes. So, and hopefully the research will then follow. And in conclusion, yeah, I'm working on the rebooting supercompiler, and I'm collecting benchmark programs. I'm hoping to create a benchmark suite like NoFib, except for supercompilers. And I'm hoping to collect some pathological cases and programs with lots of intermediate data structures. So once we have a working implementation, I'm hoping to focus on specific parts like matcher, splitter, and we have some ideas in the literature that are not tried yet on Haskell supercompiler, like homomorphic embedding or for matching. And there are some obvious improvements, like in the matcher, we compare our current term with all the terms in our history, but this can be easily parallelized, but it's not done yet. So this is one of the ideas. And then there are more experimental ideas like, can we formulate it as a search problem and apply from ideas from AI literature, for example, or profile-driven decision-making, or we can use rewrite rules, and maybe some free theorems may be helpful. So that said, thank you. And,
so it's obviously very powerful optimization. I'm wondering if it happens that supercompilation sort of fails to optimize in the way that I want to. I wonder if you have a story for how, as a programmer, I can interact with it and sort of make sure that the optimization that I want to happen actually happens. Have you thought about that?
yes, there is not a great story about that for now, but there's some work on what happens if termination checker signals us for stop to stop. In that case, sometimes, so most of the time we end up with a loop that are unrolled a couple of times, and every function in that loop is inlined. So it's a big code, but there are not much optimizations done on that code. So in that case, for example, we may want to roll back to a previous state instead of generating that bloated code. For example, there are some ideas about that. But yeah, I'm hoping to experiment with ideas like, can I mark some data types to be eliminated in compile time? So that, for example, super compiler tries hard to eliminate that. But if it can't, then it prints a warning or doesn't do anything, or yeah, ideas like that. Yes.
Does the super compiler, when it evaluates these programs, get access to the type information?
Yes. Yeah, so we work on core language. So we have some type information at core level. And in fact, we even need to do some type level computations because core has no coercions and coercions as return values and that kind of thing. So we also have that. Yes. So we have some type information at core level. That's all it is. So, yes, JC API.
So what do you need from the rest of the JC ecosystem to make this happen? How do you plan to solve the source availability problem?
Yeah, so we need in the ideal case, we need definitions from imported modules and packages. And so currently JC doesn't keep that information in interface files unless we mark definitions as inline or inlineable, or unless the definitions are not small enough. So in this case, so there are a couple of solutions for now. We have some command line argument called -f unfold all or something like that. And we may want to use that. Other than that, we don't have a solution right now. But yeah, we need some definitions from base at least. So maybe we can compile base using that argument. Yes.
What would it cost to turn that on by default? There's a lot of these optimizations that are going to need that information, right?
Sorry, what? Yes. Yeah, that's the solution.